I'm pleased to introduce Jarrod McClean from Harvard, who will be talking to us about eigenvalue solvers.
Great. I'd like to start by thanking the organizers for putting together this great workshop, and especially Steve for inviting me out to come give this talk. So I apologize in advance to the Bristol crowd, as this project is a collaboration with Bristol and especially Jeremy O'Brien's group, so there may be a bit of overlap with what you know, but hopefully it's still interesting and a different perspective nonetheless. So sort of an alternate title for this talk was, as indicated by the corny picture over here, was more about how to do quantum chemistry and variational eigenvalue problems on the quantum computer that is in your lab rather than the one that only exists in your dreams. So this was really born of sort of practical ideals and how we can reach a level where we can start to do interesting chemistry problems on quantum computers as fast as possible. So with that, I really want to tell you, since this is really a quantum algorithms kind of conference, a little bit about quantum chemistry, why we care about quantum chemistry, and what are the promises that it offers. So at the heart of quantum chemistry is you maybe have some molecule. Maybe all you know is where its nuclei are. You might have gotten this from some sort of X-ray diffraction spectra. Maybe you were given it from the protein data bank. Maybe you learned it in some other way. But from just this set of nuclei, what I'd like to do with my theory is gain some level of understanding, whether that be the absorption spectra of this molecule or material. Maybe it's the transition states that lie closest to this molecule in some reaction of interest, say how the proteins fold, how it might interact with different enzymes. Or maybe it's how it interacts with different surfaces, not only at the chemical level, but at the level of defects. And from this understanding, I'd really like to bootstrap myself into control. So if I understand the spectra, maybe I understand which parts of the molecule contributed to it, and I can start to think about designing new solar cells. If I understand all the intermediates and transition states that this reaction might undergo, maybe I can start to think about inhibiting processes that cause disease or misfolding of proteins. And if I can really understand how a molecule interacts with surface to high detail, maybe I can start to design new catalysts and get platinum out of catalytic converters and start to do some real interesting and cheap environmental science. So what is the electronic structure problem? And to some caricatured extent, it's been conjectured that it's been solved, but clearly someone is still paying me, so that's not the case. And how it was stated by Paul Dirac was that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. And the rather innocuous-looking equation that he was referring to is this simple eigenvalue problem over on the right, that h psi equals E psi. If I can find the eigenvectors and eigenvalues of this very large eigenvalue problem, then a lot of chemistry will be known to me. And essentially the mapping that I want to do is just to take some set of nuclei over here and change it into this problem and solve it. So how do chemists normally go about solving this problem? So one of the first things that we do is sort of we clamp down the nuclei and say those are so heavy that they're probably not quantum. We take the electrons, and so if you have any experience in solving, say, PDEs, you might have put things on grids before, or maybe a little bit more advanced on Galerkin type methods. But we say, actually, we're physicists or chemists, and we know a little bit more than that. We're going to say that molecules look roughly like 2 atoms or 3 atoms sitting next to each other. And so we start from things that look like exact solutions to hydrogen, and this gives us a much better, much more compact solution. Of course, this doesn't answer all the questions, so once even I've chosen these basis functions to express the electrons, I have to be careful about anti-symmetry because we know that electrons are indistinguishable fermions and things like that. And one way of taking care of that is sort of switching over to this second quantized version of our Hamiltonian, which you might not be as familiar with, but is essentially we take the physical Hamiltonian, which contains kinetic and potential energy, and we encode it into these coefficients that are functions of the nuclear coordinates. But this is essentially not really solved my problem yet. I still have, while I've reduced the number of basis functions, you know from quantum mechanics and the fact that you all study quantum algorithms that I expect there to be some exponential scaling in the exact solution of this problem. So how do we make headway into this? So the first most logical choice in physics is usually some type of mean field solution. So mathematically what I'm saying is suppose that the wave function is mostly dominated by one configuration, so one antisymmetric sort of construction of the wave function. What do I mean by this physically? Is say I have this set of electrons that I'm interested in orbiting around my molecule, and I pick out one of them. And as I'm looking at that one, and it's by no particular choice that I choose this one, I smear out the rest. And this smearing out gives me a sort of effective one electron Hamiltonian that this new electron sits in. And the solution to this gives me what are sometimes referred to as molecular orbitals. Perhaps you've seen them in an intro chemistry class before, where you fill all these levels, and these are where the one electrons sit. And so is this an adequate solution? Does it do pretty well? Yes, but is it always correct? Perhaps not. And so sometimes you need to go beyond this picture. So just to reiterate what that picture looks like, because it's sort of the foundation for all methods beyond it, is if I just have the simplest molecule I can think of, H2, and I stick one of these hydrogenic-like basis functions on each hydrogen, and I allow the electrons to occupy those levels in a mean field sense, then I can start to make physical predictions about what happens when I pull a molecule apart, how strongly it's bound. And what I want to draw your attention to is this very simple solution. As you pull it apart, it starts to do very poorly as the energy diverges. But there are some regions where this mean field solution, which is in some sense a polynomial time solution, in some sense not, I'll touch on that a little later, does extremely well. And it does extremely well in a size system that is in principle exponential. So how do we go beyond this simple mean field solution and start to get interesting physical answers? So the most conceptually straightforward way is, say I've started with this pictorial diagram that perhaps you're familiar with, perhaps not, but it's logical to assume that if this one configuration is just one that I've selected by maybe physical means, but it's not an exact solution, perhaps other configurations contribute too. And so what you can actually prove is that if you generate all of these configurations, then you span the entire antisymmetric space, and if you do a diagonalization in that space, your answer becomes exact. What's the downside? Of course, if you diagonalize in an exponentially large space, you expect an exponentially large cost. And so this is really only practical for fairly small systems. But for systems where you need high accuracy, this is the kind of solution we want to look for. And that's not to say that this is the only solution we've developed. So quantum chemists have been working for a long time on creating ways to approximate this particular solution, and in ways that you can do it in sort of realistic times. So this was a projection created some time ago in 2008, but has remained remarkably true even to date. And so down here, the exact treatment is the one I'm talking about so far, this configuration interaction, or as physicists know it, exact diagonalization. And you can see that we've developed other methods such as linear scaling, DFT, that seem to go far beyond the number of atoms which you can reliably treat as a function of year. But each of these approximate methods have some problems. So DFT has errors in transition state, charge transfer excitations, and things like that. And of course, I'm talking about practical implementations of DFT, not the formal idealized functional, which is in some way exact once you know the density. And full configuration interaction is exact, but comes with a cost. And actually, interestingly enough, we've seen a lot of interplay now from the quantum information side. So we saw a presentation yesterday about polynomial time algorithms for gapped 1D systems and algorithms related to DMRG. And very recently, these have started to make their way into quantum chemistry. And for some systems, such as like polymers that exist in 1D, these methods are extremely accurate, but they've thus far been hard to generalize to sort of arbitrary geometries or other systems of interest. But the method I want to focus on today is this exact treatment. Because if you had a choice, if you had enough resources, this is sort of the treatment you would always want to choose. And I want to convince you that quantum computers can help offer us a way forward in that respect. And so to summarize the quantum chemistry that I want you to know before I sort of move on a little bit to the quantum mechanics and the essential algorithm that I want to describe to you, is that this equation, which very simply encodes this eigenvalue problem over here, tells you almost everything about a chemical system if you can solve it. And if you could solve it exactly on these large eigenvalue problems, exact chemistry on the scale of catalysis might be within your grasp. Unfortunately, the exact solution scales exponentially in the size of the system classically, but sort of the light at the end of the tunnel, and the part particularly applicable to this workshop here, is that some instances have been identified where quantum computers can solve them in polynomial time. And to clarify there, I don't mean the problem in general. I mean specific instances of the Hamiltonian, which will become important later as we discuss the actual complexity of this algorithm. So how do we take this quantum chemistry problem and put it on a quantum computer? So in some sense, they're a little bit at odds with each other. Electrons, which are indistinguishable and antisymmetric, and qubits, which are distinguishable, and I can easily label 1 and 2. Luckily, this problem has been worked out in now a few instances. So the most general solution to this is the Jordan-Wigner transformation, which many of you might be familiar with. But if you're not, I just want to pictorially describe to you the type of encoding that we're using. So we're saying take 2 qubits, take one of these levels that I can occupy with upspin and downspin electrons, and say both up corresponds to it being empty. 1 up and 1 down is, say, the upspin electron. 1 up and the other down is, say, the downspin, and both down might be up and down. And so really this can be formalized in terms of the Jordan-Wigner transformation, but the essence of what I'm not describing here by these long operators is just keeping careful track of minus signs as I tend to commute creation and destruction operators. But what I want you to take away from this particular transformation is that it happens to preserve the number of terms in the Hamiltonian. So there were n to the 4 terms in terms of the number of basis functions of my original Hamiltonian, and there'll be n to the 4 after this transformation. But what I haven't preserved is the locality. So whereas each one before talked to roughly at most 3 of its other neighbors, or 4, this will now talk in general to across the entire system at once. And this has made digital encoding schemes one of the only options thus far, as you have to build these Jordan-Wigner ladders out of interesting sort of circuit patterns. Now, I will say that work is being done in this area, so a less non-local transformation, the so-called Bravi-Katev transformation, is now making its way into chemistry. And there's been conjectures that you can do even better than that, but no proof so far. So to give you an order of magnitude on that, this transformation goes to almost completely sort of n local terms, and the Bravi-Katev goes to sort of log n local terms. So how have we been solving this problem to date? So when we originally found out that some instances were perhaps solvable in polynomial time, what algorithm was used? And it is none other than the algorithm that is sort of at the heart of most quantum algorithms, which you suspect to have an exponential speedup over classical counterparts. And this is the sort of basic implementation of quantum phase estimation. So you start out with some eigenstate of your Hamiltonian over here. You evolve the system under your eigenstate coupled to these ancilla registers, and to grossly caricature it, you just perform some digital interferometry and read out a phase which corresponds to your energy. So each one of these steps sounds good in principle, but each of them have a little bit of practical difficulty which you encounter as soon as you start to try to put this on a real quantum computer. So the evolution part, not to belabor the scaling that is continually adjusted depending on new bounds and whatnot, but what you see is roughly that the m is the number of terms in your Hamiltonian, the k is the splitting Trotter, and t is some time you want to evolve for. So typically you get around the scaling with precision by saying that, okay, there's some finite precision I want, that exactly fixes t, and for the rest of the problem I don't worry about it. But in reality, this t to get chemical accuracy is quite large, and this corresponds to essentially extremely long coherent evolutions. So as I'm doing these evolutions, I really can't tolerate almost any error in the physical setup. So this might mean that I need to maintain coherence for on the order of minutes or hours, whereas my current architecture might be able to do microseconds or seconds. And I'll give you more exact numbers for this so you can feel the order of magnitude of this later. But the part that you do measurement on to determine the phase, of course, has some success probability, because in the idealized version, I'm feeding in an eigenstate. But if I've somehow managed to divine the eigenstate, I probably don't have a very hard problem left to solve. And so we really need to talk about what are the implications in terms of how well can I guess an eigenstate, and how well does that determine the scaling of my algorithm? Is it still polynomial time? For what instances is it polynomial time? And so starting with evolution and sort of qubit requirements, just to give you a feel for the orders of magnitude we're talking about. So this is sort of some sort of isomolecular difficulty curve. But what I want to highlight is that, say you have a simple molecule like benzene, 6 carbons, 6 hydrogens. You might expect, under a normal encoding for which you would want chemical accuracy, that this is going to require on the order of hundreds of qubits and a number of 2-qubit operations. So these are logical qubits, and a number of 2-qubit operations that are sometimes the rate determining step that's somewhere on the order of 10 to the 12. So what are current experimental capabilities? Perhaps on the order of 10 for both of these. If you're feeling optimistic or less optimistic, you might go from order 1 to order 100, depending on your order of mood. But essentially what I want to convey to you is that although this approach looks very promising, it seems like it's going to be a long time before we can put a true implementation of it onto a computer in the lab. And so to belabor this a bit further, you can just start to study what this looks like under different basis sets and different levels of precision and see more or less what you could do with this. But the outlook for the encoding and the number of operations that you would need to perform starts to look a little bit grim. So you say, okay, what can I do? And sort of this question of what can I do is what drove us to the algorithm that we sort of devised for this. And so we wanted to take what I would consider a new perspective on the problem of quantum algorithms, especially for quantum chemistry, which is that we said currently my problem is I've been given some task. And now I design a quantum circuit which is in some way optimal. Yet I take my asymptotic scaling. It's got a much smaller scaling within or some such thing, and I design a circuit for it. And then I go and I say, can I put this circuit onto my quantum computer? And the answer today is frequently I cannot. So what do I do with that? If I could put it in my computer, it might give me the answer to life and everything over here. But it's a big question mark. What happens when this algorithm doesn't fit in the computer? Do I automatically know where to chop in my circuit that I could still get some sort of reasonable answer? And so we wanted to say, is there a different way to look at it? So I'm not always interested in the exact answer in chemistry. Perhaps you wouldn't want to factor 15 into 3.2 and 5. But in chemistry, getting pretty close is good enough. And so an alternative to this is, given a task and the current architecture, can I find the best solution possible? And you have to be careful about defining the best solution possible. In chemistry, we can frequently rely on a variational principle. This might not be possible for every problem that you're interested in. And so how are we going to approach this? So what we want to do is say, in considering the architecture that we have, we want to say what is each component best at, and we want to utilize whatever that component is best at to its best extent. And so what is an easy task for a quantum computer? It turns out an easy task for a quantum computer is essentially, 1, to hold a quantum state, because that's the state it's always in, and 2, to perform some type of measurement in the computational basis. So if you can't perform a measurement in the computational basis, you probably don't have anything resembling a quantum computer. And so we sort of wanted to take this and say, okay, if I can perform this measurement and other measurements, it's sort of efficient to perform on any prepared quantum state. And in general, it may be very hard to calculate this expectation value for a classical representation. Why is that? Because it may take me exponential amounts of memory to store this state in my classical computer, which is the very real wall that you hit if you try to do some of these computations. You very quickly hit memory limits that are on the order of gigabytes or terabytes for even diatomic molecules. So this is what I would consider the strength of a quantum computer is the ability to easily store and perform simple measurements on these quantum states. And so what am I going to do to start to approach this problem? I first want to go a little bit back to basics in quantum mechanics and say, I have a variational formulation of my eigenvalue problem. This is sort of the starting point for almost every chemical approximation that we're going to make and chemists have made over a long time, which is that if I can guess some state that is parameterized in some way, maybe I can add basis functions, maybe I can adjust nonlinear parameters, then the best choice of those parameters are the ones that minimize this normalized expectation of the Hamiltonian. And since I have this Hermitian Hamiltonian, and any Hermitian Hamiltonian I can expand in terms of these Pauli operators, and actually as I showed you somewhat before, after the Jordan-Wigner transformation, this is exactly the form we have. We have a sum of n to the 4 products of Pauli operators, and by linearity, if I want the expectation of my Hamiltonian, it's just each of those measurements that I've done times some simple classical number out front that I've stored in my computer. And there's only n to the 4 of these numbers, so it's easy to store them and it's easy to compute on them, relatively speaking. And actually, for many modern methods, we can get that number down to linear because you can truncate when they become very small. And so, how am I going to proceed? Well, I recognize that there's some part of this formulation which is very easy for my quantum computer to do. I've prepared some state, and it's very good at taking measurements, right? And there's some part which is just summing a lot of numbers together, which there's a billion-dollar industry built around, known as microprocessors, which have become very, very good at summing large amounts of numbers quickly and easily. And so this sort of suggests a hybrid scheme. If I could use the best of both worlds, I could use what my quantum computer is good at and not push it too far, and I could use my classical computer for what it's good at, then maybe I could start to do quantum chemical systems on quantum computers that are in my lab today. And so if I just diagram this for you, essentially what I'm suggesting is I have some way of preparing an initial state. And I'm going to talk a little bit more about that in a second. But I put some state in. I can have any number of quantum modules operating in parallel, taking the different averages that I want. And each of those is going to produce one of those numbers I talked about. It's going to go out into my classical computer, where it will sum together and get me one number, which is the energy. And now I can take a few more points near that one, and I start to have something that looks like the energy as a function of some parameters that I'm adjusting. Maybe they're knobs, maybe they're angles on my beam splitter, maybe they're voltages on some other experimental apparatus. And I can use a traditional classical minimization algorithm like, I don't know, steepest descent if you want the simplest case, or simplex algorithm, to decide what a good new set of parameters is, feed them back in, and try to approach my ground state iteratively. And so where would you say the work is being done here? And it's really arguably in the state preparation, which I try to iteratively improve. And but not to say we can only do ground states. We can also do, to some small extent, excited states. And this is more or less a sideline, but I wanted to sort of tell you that this approach is a little bit generalizable, which is that if you just simply shift and square the original Hamiltonian, this has the effect of choosing a new ground state. Of course, there's no free lunch, right? So the downsides is this roughly squares the number of terms in the Hamiltonian, and you can accidentally cause degeneracy in the ground state. But as you sort of move this around, you imagine the state varies continuously, and you can get very good initial guesses, and this works well in practice and has in quantum chemistry for some time. So it's not just ground states. We can study the rest of the spectrum with just a simple modification. But probably the bulk of what you're wondering about is the quantum state itself. So what is the good and bad news here? The good news is in quantum chemistry, we've been studying efficient, compact, polynomially sized ansatzes for a long time. We know many good classical approximations to the ground state for many different types of problems. The bad news is if the state can be is easy to simulate classically, then it might not be that useful to put on a quantum computer, because why would I build $1 million device to do something I can do on my laptop, right? And so the downside of this is that the states we want to work with are less easy to characterize, but these are also the useful states. And so you can try to imagine what states I'm talking about here. What I'm looking for is a polynomial parameterization that can produce an interesting ground state that I cannot trivially reproduce on a classical computer. And so we have a few candidates for this, and one in particular that I think is interesting in the context of short-term quantum computation. So one of them is a unitary coupled cluster ansatz, and I don't want to belabor what this is, but it's something that is not known to be efficiently preparable on classical computers. You can do the non-unitary version, but people suspect that unitary is better, and there's a simple prescription for how to do this on a quantum computer, but for our purposes, it's still a little too expensive. So we wanted to broaden our horizons a bit and say, wait a minute, given any sort of quantum device that I have, no matter what I do, I'm going to prepare it in some sort of quantum state, and doesn't this in some way define an ansatz? And so you say, okay, you're hand-waving a little bit, but really what I want to say is that any quantum device with knobs, so under the restriction that I run the experiment twice and I can produce the same state with those same dials, then really what I have is an ansatz which is controlled directly by experimental parameters, which very likely are polynomial in number, given that some graduate student had to assemble this over a period of time. And this is really going to have some, we feel like, advantages. One of them is that the complexity of your device is almost an advantage in this case. The fact that you can't well characterize every state in your device for a large device is in some sense a property of quantum systems that you might want to look for. As I indicated before, if you could trivially describe every state coming out of your quantum system, then why would you need the quantum system at all? And moreover, this approach always satisfies a variational principle, meaning that as I turn the knobs, I can automatically detect if I've gotten a more high accuracy solution than my mean field solution, because I start with one state, measure the energy, and if the energy's gone down, I've gotten closer to the true solution, in the sense that I'm looking for the energy. And moreover, the coherence time, which I mentioned was a major bottleneck for a lot of quantum algorithms, is set by the device, not by the algorithm. Meaning that if I know that I can keep my qubits coherent for a microsecond, then I say I want the best answer that is preparable within a microsecond. I don't say that, all right, I have this long quantum algorithm, I guess I can perform a microsecond worth of it and then just stop. That's probably not going to produce a very good answer, whereas this in some way is guaranteed to produce a variationally optimal answer under some constraints. So I don't just want to talk about total abstraction here. I mentioned this was a collaboration, and so part of what we wanted to do was show that this worked in practice on quantum computers today, and a lot of you from Bristol are probably even more familiar with this quantum computer than I am. But we've chose some model systems, so a simple chemical system is helium hydride, has great astrochemical abundance, and also happens to be conveniently sized for modern quantum processors. So if you have a compact representation of this, it turns out you don't need to do the full Jordan-Wigner transformation in this case. But you can write down a simple 4x4 Hamiltonian, essentially, which is this sum of Pauli operators. And importantly, as I mentioned, we built it. And by we, I mean the collective we in this room. And so I'll give you a little bit more of a close-up of this. So what we used was an integrated photonic setup, which has this spontaneous parametric down conversion source and resistive heaters, which I'll show you their function in a second. But basically, it's a 2-qubit quantum photon quantum computer for which you can prepare arbitrary states and perform all of the measurements that I mentioned, which is essentially all you need to run our algorithm. So if you have anything resembling a setup like this, you could go back to your lab today and try to do some interesting chemistry computations. So to sort of diagram what we have here, we had this implementation I showed you before, this sort of flow chart of an algorithm. And what it looks like on the chip, if I put it on there, is that this state preparation part over here, which also performs the rotations for the averages, is controlled by these resistive heaters that sort of change the local index of refraction. And you can start to implement effective gates on your qubits. And as you do this, you can prepare the different quantum states that you'd like, perform measurements as a function of these, perform measurements and get energies as a function of these angles. And you can look for the set of angles that gets you as close as possible to the ground state. And just to highlight some of the features of this, it features a single 2-qubit entangling gate. and it produces arbitrary 2-qubit pure states with fidelity greater than 99%. And so what kind of results do you get if you start to implement this algorithm? So we wanted to look at one of the more commonly studied types of curves in quantum chemistry, which is a simple dissociation curve. If I take each of these atoms at some separation r, which is the x-axis down here, and I pull them apart, how does their energy of interaction look? So this tells me something about when I might expect a molecule to dissociate, tells me a little bit about how fast I expect to vibrate if I fit a curve, say, down to the bottom. And what you see is that, it's a little bit noisy, but we produce with nearly chemical accuracy on a lot of these points the curve that we're interested in. So basically, the approach is dominated by a few errors, but we believe that they're resolvable in some sense. So if you remember the state preparation, we rely on essentially these turning of knobs, which can sort of drift with the device. But you could imagine a digital preparation scheme, which would be just as parameterizable, but they could perhaps be error corrected in a more rigorous way. But what we were focused on was preparation of states in a way that's sort of doable today. And the grim reality of the situation is that to include error correction in a lot of these schemes today is simply too expensive to do. And so we were quite happy that we were able to perform just with averaging over the statistics an answer which can get enough accuracy. And so how does each of these minimizations proceed? So if I can do all of these computations. So a typical minimization in these cases might look like this. So I don't mean to emphasize that this non-deterministic behavior is somehow the result of noise, but it was a result of the choice of algorithm, which is the simplex algorithm. That's not the Nelder-Mead simplex is not guaranteed to have monotonic convergence. It sort of runs around the minimum and looks for a way to go down. And the reason we chose that algorithm is that noise makes derivative minimizations a little bit difficult. So what I'm showing you here is one of those points on the previous slide where I've started with actually a random initial state, and then I try to descend using my optimization procedure to the energies that the ground state energy which corresponds to this red line. And so the other red lines are the different eigenstates that you could potentially try to converge to, but we were interested in the ground state, and this has been truncated a little bit for artist rendition. It does go on for a bit further before convergence. And what I want to highlight over here on this color scale is simply that even though you may start and you may finish in a state which has very little tangle, meaning the target and initial states are not entangled, you can take advantage in this minimization of moving through states which do happen to have genuine entanglement. So you might imagine that this is going to be a requirement for any successful quantum device and quantum algorithm, given that even though some physical states might look separable, the total number of separable states is something like doubly exponentially small in the entire Hilbert space. So the ability to cross through those deserts of entanglement might still be required. And one more thing, so I wanted to get back to this problem of state preparation in a more general sense. And to do that, I want to introduce a concept called the Van Vleck catastrophe. So you may or may not have heard of this. It was referred to by Walter Kohn in his Nobel speech when he talked about the reason we needed to start thinking about density functional theory rather than wave function methods because of this problem. We haven't solved this problem in modern density functional, but it is one that persists. And the problem is stated as this. So suppose I have one water molecule, which I want to describe by some guess quantum state, psi t, and it has an exact solution, psi. And so the overlap between these two, say my guess is pretty good, is 0.9. You're like, all right, so that's good enough. I know that my algorithm will succeed with a fairly good probability. I know that the description of my quantum state is probably good enough for determining some chemical properties, perhaps not to infinite precision, but to the precision that I might expect in experiment. And now you have two molecules, and you say, okay, I'm going to use the same guess for both of those. And so how do I roughly compute the overlap of those states? It roughly squares the original overlap. So it goes down to 0.81. Still not too bad, but very quickly you can start to see where this argument's going. I'm a chemist. I'm not interested in 2 water molecules. Maybe I'm interested in 100 water molecules. And so this quickly, very quickly, as you can see, starts to become a dramatic failure. So this problem is sort of pervasive in the sense that any wave function method you use, you might expect to have this dramatic fall off. Perhaps you would hope the problem is alleviated by antisymmetry. It's not. Perhaps you'd like to consider relaxing the whole system, and in practice this doesn't actually work all that well. So what can be done about this? So this problem really enters more dramatically into phase estimation than our own, but it does enter into both problems. But what I want to emphasize is that we're not actually in competition with quantum phase estimation, but rather we sort of can help support it. So if you remember, I drew that graph before, and the number of trials that you might expect to do is related to the inverse of this overlap. So this is the part where complexity theory might tell you that you expect that if you grow this system large enough, this number of trials is going to explode, because it's very hard to pick out of thin air, except for very special systems, what the exact overlap might be, or what the exact eigenvector might be. So we're hopeful that our method, and I'll talk a little bit more about the sort of general consequences of this in a minute, but we're hopeful that for small instances, our method can even bolster the success of quantum phase estimation, because before what you essentially did was you took some default mean field guess and you plugged it in and you hoped it had really good overlap with your final state. And now we're saying that we can plug it in and I can at least do better than that mean field state, because as I drive the energy down in my optimization, I expect to get closer and closer to my ground state. And you may say, hey, that's not a proof. What if you're just converging to the first excited state? You've lowered your energy, but you haven't really increased your overlap. Well, for the purposes of chemistry, we've actually observed over a long period of time that you do, in fact, increase the overlap with the ground state. It's not a proof, I realize that, but just so you believe me, for our one trial, you can see that it very quickly converges in this same optimization, the same number of steps, to a very fast overlap. And this would increase your success probability if, after this optimization, you now have a very compact representation of your state preparation procedure that you can put into quantum phase estimation and hopefully complete a lot faster. So I promised you some treatment as to the general scaling of this problem. And I want to start by sort of prefacing the story about the mean field solution that I've been telling you about. So the mean field solution that I've been telling you about, the Hartree-Fock, that chemists use day in and day out for some 80 years now, whether it be hand crank calculators that were used originally or supercomputers used today. So this approach is sort of a nonlinear optimization that's been used time and time again at the core of, say, density functional theory. And in 2009, Verstraete and Schuch produced a proof that this algorithm was, in fact, NP-complete. And so what happened when that proof came out? Did the whole of chemists sort of stop using Hartree-Fock? No. They just sort of conjectured that either this fact was not that important for our instances, or perhaps there's something special about quantum chemical problems that makes them the easy instances of this NP-complete problem. And so why exactly we're able to do so well? In fact, most of the things I've been talking about are extremely expensive techniques to recover the last 5% of the energy. We, in fact, usually get 95% of the right answer with just the mean field. And so what I'm trying to say is that, is there something special about chemistry? Perhaps not. Perhaps there is. But we saw many presentations yesterday about how the local Hamiltonian problem we expect for these, and I believe it's been proven for the quantum chemistry Hamiltonian, is QMA complete. And so you may say, why are you trying to solve QMA complete problems? Well, we don't get to choose the problem we want. We get to sort of, physics gave it to us and we do the best we can. And the fact is we've been doing extremely well on this QMA complete problem. Will our luck run out at some point? Perhaps. But I would say that the only way to know is the way that we've known in previous approaches, which is to actually start trying to do these algorithms and see if they work. And you can't actually start to test these algorithms if the hardware requirements tell you can't look at them for 30 years. So what I've hoped to have done here is actually create an algorithm where you can start to start to examine whether these problems are actually present in these systems, whether we can push forward as we've pushed forward in the past. And I think we've reached a nice place where we can do that, and we can start to put this on any given quantum computer and really say, does chemistry suffer from this catastrophic problem or not as we go forward to the sort of quantum frontier. And so just to summarize, I want to say that considering both the problem and the available architecture offers a new way to utilize quantum resources today. A small-scale implementation has been built and tested. We are complementary in every way to previous quantum algorithms in the sense that you could just stop our algorithm at some point and use it as a state preparation prescription. And we think it's a promising approach for quantum computers in the lab today, which we hope will offer an avenue to sort of vet the hypothesis that quantum computers are going to be able to facilitate large-scale, accurate quantum chemistry calculations. And I'd also like to, of course, acknowledge the big players in this. From our own university, my boss here, and Man Hong, who is now a professor in China. And of course, we have one of the members in the audience, Sao Chi, and our other collaborators at Bristol, even though Alberto has since moved on to Sydney. And I believe was asked to leave 20 minutes for questions, so hopefully that's not too optimistic, but thank you all for listening. Yes?
Isn't this approach intrinsically not scalable? Because as you increase the size of the problem, the Hilbert space is going up exponentially. And with your experimental knobs, you've just got a polynomial number of knobs. So you're exploring a polynomial dimension manifold in this exponentially large Hilbert space. And there's no reason that it should get any place closer or much closer to the ground state than you initially started with.
So for a completely arbitrary problem, I might agree with you in this sense. But luckily, sort of quantum chemistry is predicated on the sort of idea that we can get very close to this exact solution. So in some sense, we're not trying to start from a totally random point blind and walk this global exponential space. The situation is more frequently that I've gotten 95% of the way to my solution, and now I just need to finish the walk. So in some sense, though, you open an interesting question, which is that for any quantum algorithm, what I'm asking for is a set of a polynomial number of parameters that puts out an answer in this exponentially large space that is relevant to me. And normally we see this in the form of gates, right? Like I would write down a gate sequence, which would hopefully be polynomial in length if it's interesting. And what this constitutes is a polynomial number of parameters that's getting me to a state in an exponentially large space, which hopefully encodes my answer. So that's one part of the answer, is that we believe that they're based on the quantum algorithms that have been made in the past and based on quantum chemistry that we're hopefully in this region where we can solve the problem. And what we're really depending on in our case is actually the history of quantum chemistry, which is that, we've always been tackling this problem in an exponentially large space, and we believe that we have very good guesses on how to get very close. So it's kind of strange, as soon as you tell someone you're doing a large nonlinear optimization, they very want to sort of throw up their hands and say, what are you wasting your time for? This is not really going to get to the solution. But surprisingly, for some 80 years now, we've been doing these complicated nonlinear optimizations in chemistry, in coupled cluster and multi-reference theory that do nonlinear, sometimes ill-conditioned optimizations on hundreds of thousands to millions of parameters simultaneously. And we attain results that are sometimes accurate to 6 or 7 decimal places. So whether this is a fluke to our classical methods or a trend that can continue, I think is a valid question. But I think it's historically been one that we can only evaluate after the fact, which makes this actually a very hard problem to answer. So I hope that's good. Either one. Yeah.
In your example trajectory, your sort of goal eigenstate was product state. Is that a feature of the particular problem you've chosen, or is that a generic feature in problems of this kind?
So this was sort of a generic feature, a feature of the problem that we chose. And actually, it's also a feature of the geometry that we chose. So in a broad sense, this is actually very close to the case for chemical systems which are near equilibrium. So if we have sort of a distinction between an idea of statically correlated and dynamically correlated, and we can talk about that afterwards, but for most dynamically correlated systems like this one near equilibrium, the system is sort of 99% a product state and 1% a little bit trailing otherwise. And you say, okay, why aren't you satisfied with the 99%? Well, it turns out that last 1% frequently has the bond energy in it that you're interested in. And so we have ways of recovering this, but we would like to do so more accurately. And also there are cases, if I take that same molecule and I stretch it apart, sort of as you stretch it apart, you get the equivalent of entanglement between the electrons on either atom. And if you pull a very large system apart at every bond, you can very rapidly produce a state which looks nothing like a product state. And so, yeah, Steve?
So you have this experimental ansatz for the space states you can explore. Is it possible to say anything beforehand that this will be a good experiment? Or like if someone says, here's a proposal for a $2 million experiment, can you say something beforehand that this will explore an interesting space?
Well, I think it's a very interesting question, and it's largely going to be dependent on the device that you've built. So you hopefully, while you're building it, you have some idea of the states that it's likely to prepare. Usually, in the short term, they're not going to be universal, right? So you expect that it can prepare some small subset of states. And one of the things we are looking into is that we're hoping to appeal to physical similarity between the sort of apparatus that we're building and the sort of molecules we're interested in. And so I don't have a lot of good examples of this yet, but recent work we did, we tried to say that, ion traps happen to have natural vibrational modes in them. Molecules happen to have vibrational modes in them that we'd like to study quantum mechanically. So if I make one of these sort of generalized parameters a way I can just directly encode vibrational modes from my molecule into the ones in my trap, then I've sort of completed one part of that parameterization, and I can start to look at the rest, the electronic parts. But in general, I think it's a hard question. I'm interested in ways to start to study. For example, if you give me an arbitrary quantum system, can I tell you what classes of states it can produce? Can I tell you how close this is to the states that I'm interested in? But I think it's going to be, in many cases, as challenging as solving the original problem itself. So for small apparatus, probably to the order of 20 to 30 qubits, with some elbow grease, you might be able to characterize all of the states and make some really concrete statements. But once you've entered the regime of truly interesting states that you don't know if you can produce them on your classical computer, say in the 60 to 100 to 200 qubit range, I don't yet know how we're going to actually start to explore those. So, yeah.
So early on, you mentioned the big problem that chemists want to solve is, given Hamiltonian, what are the eigenvalues and eigenvectors?
Yes.
So in some sense, is this the problem that people really want to solve, or do they want to, maybe extract some properties about the ground state? Or, it's a very, very sort of general question, but if you said to them, okay, here's a quantum circuit which outputs the ground state, and I tell you this is the ground state energy, will they be satisfied with this, or do they want to say, well, actually, I don't really care about this quantum circuit. What I want to know is some physical properties of this system. Or I guess what I'm getting at is that is there maybe some simpler problem which is kind of more interesting for people to solve in practice, or potentially simpler problem.
So it's a great question, because a lot of what we're looking at is sort of these ground states, these quantum states that I've prepared. Are they useful? Is there a faster way to get just to the properties? And so the short answer is that this is sort of the best way we know of to get at a lot of the properties that we know. So if you can prepare these quantum states, then we sort of know how to extract the relevant information from them. And there have been a lot of very good approaches to sort of skirting this problem with better numerical properties, but ultimately we've always seen that the scaling is roughly the same. So you might expect that if I'm looking for an energy difference, if I can converge directly on the energy difference or excitation energy, rather than doing each independently and putting them together and trying to slap everything together, I might do better. And that's the case, but ultimately as you go to larger systems, you win only in more or less a prefactor, sometimes a very large prefactor, but not one that really saves you from a problem of exponential scaling as you grow and grow your system. And so, yeah. But there have been, and there's ongoing attempts to actually encode more of this problem into like directly looking at physical observables in quantum computers. And to some extent, quantum computers are very well suited for some of the approaches we have based on time dynamics. So if you think about what quantum phase estimation is, it's recognizing that given any initial state, really what I'm good at is just encoding a quantum state and letting it evolve somewhere. The hard part is in the measurement. So if I can gain interesting information on just how my quantum states evolve, then I'm much better off than if I need to absolutely prepare this eigenstate. And this is one of the things that we're excited about, in the sense that the spectrum of phase estimation, regardless of how bad my initial state was, if I can have some inkling as to what the state might look like initially, then I can still gain a lot of information, and I can still have a fairly good promise that it's not going to cost me exponentially. So, thanks. Any other questions?
So that may be sort of my misunderstanding, but if you're using these techniques to get basically close to the answer classically, and you want to use the quantum techniques to get closer, but if you, for example, scale it up and get to a stage where you have much more complicated molecules, does this technique, do you always know that you are basically improving the approximation, or is there because for now, at least to me, it seems like you are comparing to what you basically already sort of know and see that it's sort of better or close. But if you don't know that, if you want to actually find out for the first time because you have a more complicated system, does that technique, how much basically trust do you have in the performance of the quantum computer?
So it's a great question in terms of how to sort of falls under the general heading of sort of verification and validation of sort of computer simulations in general. Once you've gotten to a scale where this is the first time you're ever doing this computation and no one can repeat it. And for our specific case, I think frequently we're interested in the energy, and to some extent the variational principle tells us that we're lowering the error in energy. But as you pointed out, does that necessarily mean we're lowering the error in the quantum state? And for right now, the only tools we have available to us are the history in solving these problems, which is that you expect as you lower the energy to sort of shift the population from higher excited states into some of the ones that are lower than the mean field, but that might not be the exact state you're interested in. So this is sort of error that we have to consider acceptable, and the gauge that we typically use when you develop a new method whose performance you don't actually know how to characterize to every decimal is comparison to our previous benchmark methods. So because of this variational principle, I can go out and I can use my best classical method, and if my quantum method doesn't give me an energy lower than that, then I know that there's no way that it's more accurate than my classical method, especially if I'm interested in the energy. And if we can consistently produce energies that are below my known variational classical energies, then you can have a pretty good confidence that you're in some way doing better than you did before. And so that in some way is an undeveloped answer. Every method after its creation has had diagnostics built for it, and these systems will similarly need to have diagnostics in the sense that, if I measure these values and I find that they're errant with respect to these, then I might not have a high confidence in my answer. But to answer your question, ongoing work and basing it on previous known results. So.
Right. Well, if there are no more questions, let's thank the speaker again.